startups and researchers that are addressing space healthcare risks and mitigating them and finding ways to mitigate them. Before I start, once again, congratulations to all the first round winners of the 2024 Humans in Space Challenge. And we cannot wait to hear your ideas. But before that, I want to thank everyone here on behalf of Orion. So to briefly share with you how today's program would flow, starting with a brief introduction of the Humans in Space program, we will be introducing the esteemed evaluators for today's pitch. We will then move quickly to the presentations of equity investment applicants. We'll also have a short break in between as well, followed by presentations from the Orbital launch funding applicants, or those teams that are planning to send their experiments to space through the Humans in Space funding. So without further ado, it is my pleasure, really a big pleasure to share with everyone what the Humans in Space Challenge is all about. So the Humans in Space Challenge is a global space healthcare challenge that calls for startups and researchers that are addressing critical health problems in space and on Earth. So the program provides a platform for startups and researchers who are either addressing healthcare problems faced by astronauts or developing breakthrough healthcare solutions for Earth by leveraging the microgravity environment to come together and share their idea. So ran in the format of a challenge, the program provides a platform for interaction with esteemed leaders within the space healthcare field as evaluators or mentors. We also provide curated accelerator program for the final winners and a network of investors and collaborators. So on the screen, you'll see some of the highlight pictures from last year's final pitch at Ascend. And this year, the winners that are selected through the virtual pitch day will be presenting live at IAC. Another exciting factor about the Humans in Space program is, of course, the award. So the final winners are awarded with either $50,000 of equity investment or up to $250,000 of orbital launch funding to send their experiments in space. And in doing so, they're supported with other benefits, such as access to exclusive networking events, Amazon credits, alumni connection, and international promotion or exposure, especially through their final pitch at IAC. So through today's virtual pitch day, we are going to determine the second round winners that will be presenting live at 2024 IAC. And to help us determine these winners, we have invited 8 evaluators to join us today. They're indeed leaders of space healthcare from both research and commercialization sector. So it is my great pleasure to introduce to you the evaluators for Day 2, his virtual pitch day. First, Stephanie Schablom, Vice President of Strategy and Business Development of Aurelia Institute. Dr. Israel Biran, General Partner of Earth and Beyond Ventures. Dr. Patrick Hollis, CEO of LightGrav. Dr. Ken Savin, Chief Scientist of Redwire. Dr. Paul Camoon, Chief Marketing and Business Development Officer of Space Pharma. We have Cesare Robascio, Space Exploration and Science Innovation Lead of Thales Alenia Space. And Kevin Sprudge, CEO of Zero Gravity. And Martina Trusch, Space Medicine Entrepreneur and Consultant. So these amazing panel of judges, as well as the Humans in Space evaluating team that is not on the screen right now, will be evaluating your pitches today. All right, I hope everyone is ready. Again, just a reminder for the presenters, you have 5 minutes to pitch your ideas, and then we're going to move on to the 3-minute Q&A sessions with the judges. Judges, if you have any questions that you want to ask, please use the raise hand feature on Zoom, and I will moderate you into the question. Because of the time limiting factor, we will be very strict on time, and in case and we won't be accepting any more new questions when we reach last 10 seconds of your Q&A session. We ask for everyone's understanding on that. All right, I'm really excited to hear all the ideas that are being presented today. First, we're going to start with presentations from the equity investment track. And for the first presenter of the Humans in Space Virtual Pitch Day, Day 2, we have Reconnect SAS. So Reconnect SAS is a startup based in France that specializes in AI-based pharmaceutical development and biotechnology data analysis. Please welcome to the stage Cyril Wayon-Boyant, the CEO and co-founder of Reconnect SAS. Take away the stage, Cyril.
Good morning, everybody. So I will try to advance the slides. Okay. So I'm very pleased today to present you Manta by OneTrack. So this is a specific device that we are building, and we wish it to revolutionize the healthcare in space. We do believe that this will be a strategic asset for Boeing company. We are already proudly supported by BHDN, MEDES, ESA, Airbus, and a couple of fellows in France. And so now, without waiting too much, I will tell you what's the issue we are trying to solve. So the issue that we are trying to solve is that very vulnerable humans are sent to space, and they can jeopardize space mission because of problem of healthcare, obviously. And this is due to the physiological complexities of space missions. And also, there are very few treatments that are known for space-associated disease, such as bone resorption or muscle atrophy, as you know. So the device that we developed is a software and hardware combination. So this is called Manta by OneTrack, and it allows you to build personal astronaut digital twins for running autonomous diagnostics and identification very quickly of treatment avenues. So how does it work? And so we do believe that this is a strategic asset for Boeing Space Healthcare vision. First, it aligns totally with Boeing's goals of advancing space healthcare through autonomous diagnostics and personalized treatment options. Second, it is an unmatched innovation because we can leverage more than 8,000 disease progression models and personalized digital twins, which offers a unique edge in space-specific treatment development. We believe that it can enhance the R&D capabilities of Boeing because it can accelerate discovery and validation of new molecules, which reduces the time to market and boosts clinical trial success rates. This is also a strategic market expansion possibilities because beyond the space healthcare, Manta by OneTrack could open new opportunities in telemedicine, which support Boeing's broader business goals on Earth. So it relies on several pillars. It brings personalized medicine with one astronaut equal one digital twins. This is precision medicine. This is also somehow predictive medicine. And you can adapt that to various monitoring environments such as omics, semantics, imaging system. And it brings safer treatments because it generates leads and mechanism of action for repurposing avenues of existing molecules with known drugs and control side effects for various indications. If I may, I would say that we are really in the healthcare for space market. We do have, of course, a driver with the deep space exploration, colonies, and tourism that is foreseen. But there are also several spillovers on Earth that we can foresee, especially to solve EV needs in medical deserts. This is highly translatable to Earth, like I said. In the future, and this is an option. There are several of KPIs that I want to skim and through. So we do foresee to identify 3 to 5 new molecules annually for space-induced diseases. We do foresee royalty incomes for 10 million annual at the cruise speed for commercialization of new treatments. We do foresee market penetration of 10% market share in space healthcare, and this is an option of 5% share in global telemedicine by year 5. We will use the strategic partnership with MEDES, BHGN, and ESA, as well as with Airbus, other key players to minimize the risks and to maximize the market entry success. We do foresee a couple of projections in revenue, up to 50 million for market dominance in year 5, and expansion and commercialization of new molecules, mainly with a joint venture or co-development of molecules. We already have traction and validation of our work with more than 80 different clients on Earth, in partnership with Airbus, and really cool exchange with Space Pharma as MEDES. We do have a first flight foreseen in 2025. And the last slide that I will present you, this is the team. So the team is super knowledgeable in physiological and data science. For that, we do have a good business board and a fantastic science board as well to help us. And my wish today, this is that Reconnect and Boyon can work hand in hand for equity and co-development of leads. Thank you very much for your attention. Thank you very much for the organization. My name is Sylvian Boyon, and that was Manta by OneTrack.
Yes, thank you very much for that pitch, Cyril. Now the floor will be open to the judges to ask questions for 3 minutes. Judges, if you have any questions, please use the raise hand feature to ask questions. Yes, Stephanie.
Good morning. Thank you for that presentation. Would you mind clarifying, is Manta a device? Is it a hardware? Is it a software? What is the exact thing that Manta is?
Well, this is a cool question. I love it. So for the last 6 months, 1 year, and something like this, it was just a software, and we realized that this would be really cool to encapsulate that directly on a personal computer, a super, very frugal in energy and computational capacity, a computer. So this is a mix. This is a combo between a hardware and a software thing.
Okay, got it.
Thank you. Yes, Martina.
Can you please comment on what differentiates you from other similar companies? And also, can you elaborate on your Earth applications? What is your revenue from all these partnerships that you have?
So I'll try to answer that very synthetically because I can't hear you properly. But I think that the first question is about the differentiation. Differentiation, this is that we are building digital twins, and we are integrating multimodal data. So it can be omics, semantics, it can be many kinds of data. And that, to our knowledge, this is not something that is doable by other company. The second thing comes from the hardware. So this is a hardware that is not using cloud computing. This is all of the computing is very frugal, and this is based on the PC, on the personal computer, that we do not see that elsewhere. So this is the 2 main things that I would say that are really differentiating us from the other company. Many kind of data that can be used to make the digital twin very specific, and this is autonomous and resilient. You can use that on a personal computer. The second question that you had, this is the sources of revenues. So for now, we are using many preclinical and clinical services that we are running with Manta for now. So we already generate revenue by now. But what we foresee, this is that we can use, we really want to find partners like Boyon Company to co-develop molecules and to have royalties coming from the patents that we would make on the identified leads and the identified mechanism of action that we would find. So this is something actually that was proposed to us by our partner at EY Parthenon, Omer Saka.
Thank you very much. So due to time constraint, we'll have the last question from Dr. Ken Savin.
I don't think we're going to get through it, but how do you find molecules? You said you're finding new molecular entities. How are you doing that?
So very quickly, not new molecule, repurpose the molecules. So they exist.
Okay, so you're finding old compounds and reassigning. Okay.
Thank you very much. Thank you, Cyril, and thank you, judges, again for joining us. Now moving on
Thank
to
you
the
very much.
second part. Thank you. Now moving on to the second presentation for today, we're going to invite to the stage Gravity X Bio. So a brief background, Gravity X Bio is an early stage startup based in Ireland that focuses on innovative research in development of breast cancer treatment under microgravity condition. So please welcome to the stage Dilip Kumar, the CEO and founder of Gravity X Bio.
Oh, can I start? Is it audible? Okay.
Yes,
Yep.
please start.
Good afternoon, everyone. It's my honor to introduce my startup called GravityX.bio. What we do, we both combine microgravity grown patient-specific breast cancer 3D models and AI to translate drugs to clinical success. The problem is every 14 seconds, a woman somewhere in the world diagnosed with breast cancer, and more than 2.3 million new cases of breast cancer diagnosed, and 670,000 deaths already occurred due to breast cancer in 2022 alone. Despite significant advancement in medical science, 90% of drugs fail to reach to the market. This is mainly happens at the preclinical stage, and the main problem is they depend on traditionally available 2D and 3D cell culture models. The problem with 3D models are they're not repeatable, reproducible, and fail to replicate complexity of human tumor and inconsistent diffusion of nutrients and oxygen. Addressing these challenges need advanced preclinical models, and even NASA said that a 10% improvement in failure prediction could save $100 million every year to this company. To solve this problem, we are introduced a microgravity grown 3D breast cancer models, and also we screen drugs to these models to ensure targeted treatments and minimize potential side effects, and want to provide alternative to animal testing. This is possible because space provides weightlessness, natural vacuum, extreme temperature range, no contamination, and flawless mixing. How we do that one? By growing in a tumor on a chip microfluidic system. Please allow me how this works. A short video. So this is our tumor on a chip model 96 well plate. Here we can place drug or drug combinations. Here we can place 3D breast cancer model to grow, and screening happens. Thank you so much. The impact is a novelty breakthrough approves for biological barrier in vitro. In terms of innovative technology, we can grow 32 different breast cancer models, and we can simultaneously test the drugs against these models in real time in space. The significance is in space, unique environment to grow 3D cancer models and new therapeutic approaches for effective cancer treatments. We enhance drug discovery by reducing failure rates here on Earth, and in terms of cost, we can minimize the animal usage. Why us? My name is Dilip Kumar, founder and CEO. I have a PhD in pharmaceutical chemistry and formulations, and my supervisors already have microgravity research, worked with NASA and Italian Space Agency. My CTO is a serial entrepreneur, and these partners are helping us to launch experiment into the space and doing the analysis by AI. And we want to collaborate with HIS for exclusively focus on oncology and personalized medicine to collaborate our technology with them. And we want to tap their networks, zero gravity flight opportunities to expose ourselves internationally. Our business model, we are B2B, microgravity as a service. First, we target customer, do experiments here on Earth to collect the preliminary data. Then we launch experiment into space. Then we collect even further data. In terms of revenue, we engage in exclusively contracts for drug screening, if possible, revenue sharing and royalty agreement. And on screen, you can see one of the drugs sold by Pfizer in 2023 for $4.75 billion. It's a huge amount. And market opportunity, I'm going after 1.3 billion service obtainable market, which is 20% of market of service available, and it is 9.3 billion, and total market itself is a 32 billion. In terms of value, we are introducing a new category in this industry by competing against traditional 3D models and animal models. And we have provide 3D models, drug efficacy, and reduce time to 18 months and cost to 35%. We are using both generative AI and microgravity to accelerate breast cancer drug discovery. In short-term goals, 2 to 3 contracts with partnership, pilot project with hospitals. Challenges still there, market acceptance, funding, and regulations. And we expecting revenue 150 to 500, securing need to 100,000, and already secured 50,000. And long-term goal, global expansion, product diversification, scaling production challenges, competition there, but expecting 10 million year 3 positive. Thank you so much. We're working with a purpose, vision, and mission. Thank you for your time.
Thank you, Dilip, for the wonderful presentation. Now we're going to move on to the Q&A sessions. Judges, if you have any questions, now is the time to ask. Yes, Martina.
I'm curious, is this approach more or less applicable to different subtypes of breast cancer and different stages?
First of all, we are not working on different subtypes because it's too much work for us. First, we are looking into HER2 or triple breast cancer as an initial goal.
Thank you. Thank you, Martina. Yes, Cesare?
Yes, thanks for the presentation. Do you have plans for in-space experiment?
Yep. I'm in contact with the NanoRax for the past 2 months, and we are developing a hardware. And I already had a meeting yesterday. And if everything goes well, by Feb 2025, we want to launch an experiment in space. Isabik is supporting.
Thank you very much, Cesare. We do have a question from the Humans in Space Evaluating team. We understand that your company, we would like to better understand the company's current IP status. If there are any existing IPs or any future plans.
We took license for that plate. That is only one thing. And in future, once the experiment is successful, then we can develop IPs and patents based upon the hardware, the procedure, the methodology, what we are applying into the space to grow these 3D models and test drugs against it.
Understood. Another follow-up question is, we understand that your team has a couple of members involved in in-space experiment. Could you further elaborate on the team's capability for expanding your business in the space field?
Yeah, I contacted them. One is from Switzerland, one is from Italy. They have vast experience in this field. They are acting as advisory members for initial experiments to help me to promote my startup to the global level. That's their role initially. But once my startup take off, then we can raise funding and we can whether give us some equity or we can hire a new people to even further accelerate our progress.
Understood. Right. If there are no questions from further questions, we will now close the Q&A session. Thank you very much, Dilip, for that wonderful pitch. And thank you, judges, once again for joining us. So the next presenter is CFO company. So CFO is a startup company based in South Korea that develops stem cell-based cell therapy for intractable diseases. Please welcome to the stage Hyun-Suk Park, CEO and founder of CFO. Hyun-Suk, when you're ready, please feel free to turn on your camera and share your pitch.
Okay. Hello. Hello, everyone. I'm Hyun-Suk Park from CFO. At CFO, we develop innovative tools and solutions to address bone weakness in space. Our patented culture platform produces bone-forming cells from stem cells, and which is in clinical trials for bone necrosis. We have also created a breakthrough bone organoid model mimicking in vivo bone conditions with a QD square cell tagging system. Additionally, sericin, the health functional food candidate, is designed to prevent osteoporosis, which is crucial for maintaining bone health in space. Problem and solutions. With limited space on the ISS, alternative methods are needed to replace animal experiment. Our miniaturized 3D bone organoids allow detailed studies of bone metabolism in microgravity with key cellular interactions tracked by our tagging system. In vitro organoid studies will be paired with in vivo trials on Earth and in space to validate sericin's efficacy. Scientific merit of this project is first our bone organoid model with comprehensive cellular composition, and secondly, scalability overcoming space constraint. The third, rigorous in vitro and in vivo testing of sericin, potentially revolutionizing bone health, benefiting both space exploration and terrestrial medicine. So our team is composed of multidisciplinary scientists. Experimentation is as follows. Hydrogel-based bone organoids are cultured with or without sericin and in the presence or absence of microgravity. Bone formation and resorption are analyzed in the mediums Rankle and OPG ratio, or CTX and C1-MP ratios. Collaborating with research operation and integration team and the Human Health Countermeasures Program, similar measurements are taken from astronaut blood samples post-space travel with or without sericin. This parallel in vitro and in vivo study assesses sericin's efficacy. Business model are two. One is a health functional food to support bone health in space and on Earth, offering preventive benefits during space missions. The second one is bone organoid model and contract research service for academic and commercial research. Our revenue model includes licensing, B2B service, and B2C marketing. Target market and customers. Bone health functional food on Earth, offering bone health aging prevention solutions. The market is $2 million in Korea in 2023, with the global market projected at $418 billion by 2028, with an 8.79% CAGR. And bone health functional food in space targeting astronauts and bone organoid model with for customized contract research service. So our value position is in extreme environment. So with rigorously tested in space, confirming their effectiveness and reliability, and the comprehensive application products from Earth gravity to microgravity support bone health. Okay. Our business milestone is that in short term, in 2025, we will launch sericin functional food, and in 2026, we will obtain individual authorization from MFDS in Korea. And until 2027, we will standardize and commercialize three-dimensional bone organoid model. Thank you very much for your attention.
Thank you very much, Hyun-Suk Park. We will now move on to the Q&A session. Yes. Yes, Patrick, please feel free to share your question.
Thank you. I'm curious about the form of this functional food, the consumer-facing form. Is it a powder or liquid? What is basically the exact formulation? And the second question is, have you looked into as a potential business model to offer the functional food testing for space applications? Because it looks like that you have a good assay to actually test these formulations for space applications.
Okay. Here the final formulation is what is it, like a jelly type, because which is very easy to carry on, and even to what is it, having even in the space. So the final the formulation we are preparing in the jelly form. So what is your second question?
Second is the formal. Do you have also IP over the formulation? So is it like orally absorbent? And would you co-develop maybe other functional food with other research institutions and companies as a service?
Oh, actually, this license is a licensed from a certain university. So this patent is related to the what is it? Their function only. So the formulation, we didn't make a patent for it. So this is a very novel approach. So nobody have tried sericin for the bone to prevent the osteoporosis, but we have a very solid evidence for that.
Thank you.
Thank you, Patrick. I think that was a really good question. Yes, Cesare?
Thanks for a nice presentation. My question is related to the fact that, astronauts work typically for the agencies so far. Do you have any contact with any space agency for, potential delivery of your formulation to astronauts?
Yes, we have some people in contact, because we have a plan to make a laboratory in Japan. So we contact the people, Space BD and the JAXA in Japan.
Thank you.
Thank you very much. If there are no further questions, we will end the Q&A session now. Thank you very much, Hyun-suk, for joining us today. And thank you, judges, again.
Okay, thank you.
We will now move on to the fourth presentation for today. The fourth presenter is a company called Inhale. Inhale is an Israeli startup that develops innovative air sterilization device based on hydroxyl radical generation. So please welcome to the stage Itai Benartzi, founder and CEO of Inhale.
Hi, everybody. Imagine a world where hospital infections are a thing of the past, and humanity can safely explore the stars while Inhale is providing just that. At Inhale, we engineer air in closed spaces, closed environments with natural hydroxy radicals that leading to continuous, safe, and effective disinfection of air and surfaces in the presence of humans. We're creating always safe environments on Earth, in the air, and beyond into space ventures. Hospital-acquired infections threaten billion hospital patients annually. Approximately 100 million will acquire infections and 6 million will die. Surface-borne infections account for most of the problems, but still are left unresolved. But really, this is even more dangerous. The International Space Station is even more dangerous due to increased virulence, biofilm formation, and microgravity and contaminations. Long duration missions expose crew to closed environments where unknown infections could have severe consequences far from medical support. And existing solutions? Well, we cannot count on a series of one-time actions to save us. Existing solutions have been proven ineffective here on Earth and are not compatible with space environments. they're either toxic to humans or provide only a very localized efficiency. And don't we deserve a solution that will keep us safe all the time? What we're missing is hydroxyl radicals. Hydroxyl radicals are naturally generated in our immediate atmosphere as UVC meets ozone and water vapor. This is Earth's natural detergent responsible for the disinfection of microorganisms and VOCs and the decomposition of pollutants. Unfortunately, hydroxyls are not generated indoors. Natural outdoor levels is 10 to the 8th, and Earth hospitals have 10 to the 4th, and the ISS has approximately 10 to the 2nd. Well, hydroxyl in proper concentrations could save us indoors, and this has been sought after by NASA, but so far unsuccessfully. Sorry. Yeah. Well, inhale generates 10 to the 10th and infinite amount of hydroxyl radicals without unsafe, cancerous ozone residues, which have previously limited generation attempts to 10 to the 6th. These are carried through any ventilation system, engineering air to resemble Earth's atmosphere anywhere. And inhale is really disrupting the $60 billion broken infection market. It's the only solution that allows hospitals and clinics complete, continuous, and effective disinfection coverage 24/7. A third of US hospitals are constantly seeking new disinfection solutions, clearly unsatisfied with existing options. And with an annual subscription, any 4,000 square feet space could enjoy inhale at any given time. Our team includes 5 PhDs with expertise in atmospheric chemistry, microbiology, healthcare, and air quality, combining over 100 years of experience, including space tech. And basically, Inhale's technology has been proven effective in lab conditions, generating ozone-free hydroxyls. The company was chosen for Creation Space's accelerator and installed our working prototype in 2 departments as part of an ongoing paid pilot with an Israeli hospital, leading to continuous disinfection in the presence of patients. We have that in data. We've secured $450K from angels and expect a 400 grant to come soon, and aim to raise a $3 million for the next 24 months to take this technology to market and to space. Our biggest challenge is maintaining the disinfection effect in complex environments, which require monitoring and maintenance and adjustments of the hydroxyl concentration, given what we're facing in the space we're dealing with. Yeah, we need safe and healthy environments with natural hydroxyls for humanity to expand into space. Inhale provides this fundamental infrastructure, dramatically increasing our chances of thriving on Earth and beyond. We hope you could join us as strategic partners or lead investors to help bring this groundbreaking technology to hospitals and space missions worldwide. Thank you very much.
Thank you very much for that pitch, Ty. Now we will quickly move on to the Q&A session. Judges, if you have any questions, please feel free to raise your hand and I will moderate you into the session. Yes, Dr. Paul Kamoun. I think you're muted.
Yes, hello. Thank you very much for this very nice presentation. I have a question concerning your existing or not existing contacts with space agencies already, or with NASA in particular. Did you already start proposing your system and technology?
So we have had a few conversations with NASA and actually some people with Thales Alenia as well. But this has been the only thing we've done so far. We're really early steps given space agencies, but they show enthusiasm, so as we.
Thank you.
Thank you very much. Thank you very much. Yes, Dr. Ken Seven.
What is the mechanism by which you're making the free radicals?
Well, it is pentazoic. Feel free to explain about that. Basically, we're generating big amounts of ozone in a box and converting almost 100%, 99.85% of that ozone into hydroxy radicals and other reactive oxygen species. All are fully safe to be used among humans.
Yes. Thank you for that question, Dr. Ken Savin. Yes, Martina?
Can you please comment on the consistency of your solution? Because I thought it was gas, but then your visuals had a liquid and a spray, so I'm not sure. And
No.
also, how do you plan on testing it?
So the machine, basically, as we do now in hospitals, the machine is set on the roof or the AC HVAC room of the hospital. Working from there, dispersing hydroxy radicals into the room through any ventilation system. So this is a gas phase solution, basically enriching air, similar to what happens outdoors. And your other question was about a business model, was it?
How do you plan on testing it? Like the logistics, right? Like, because you're on International Space Station, so first you need to test it, and once you test it, you will be applying it fully. So how do you plan on implementing?
So we've already tested it on Earth and in lab conditions and in a hospital, showing continuous disinfection of surfaces through the air ventilation system. The test in orbit or in space would be much different because we have to take in consideration the different air composition that happens in space, and we have to plan for that, and that will take us time. That's a big challenge.
Thank you. I think that was a really great question. Yes, thank you, Martina. Thank you, Itai. So that is it for the Q&A session. Thank you again, Itai and the
Thank you
judges
very
for
much.
joining us.
Thank you.
We have one last team presenting before our break. The next team is Precision Payloads, which is a US startup that started out as a spin-out of space medicine organization called BioAstra. They provide bioinformatics analysis and personalized medical kits for astronauts. So please welcome to the stage Savi Glowy, CEO of Precision Payloads.
Hello, thank you. Wow, what a fun morning. Everybody's done such incredible presentations. What a great group. My name is Savi Glow. I am here on behalf of Precision Payloads, a BioAstra 501c3 spinout. Precision Payloads is building personalized health medicine packs for astronauts for their training, in-flight mission, and post-flight recovery. Our genetics make us who we are. From the way we look to the way we metabolize medicine and drugs. And I'm so sorry, my slides are not advancing. Anyways, we have seen space has changed. Space changes our genetics. I'm so sorry. I don't know why my slides are not moving forward. There we go. Space changes our genes from, oh, here we go. They all caught up. There we go. We see structural metabolic changes, chronic inflammation, increased stress markers. And while clinical utility of personalized genetic medicine on Earth, precision medicine, is widely used today, precision medicine is not being used in space to prevent or respond to these increased risks. At Precision Payloads, we are building personalized health kits with luxury finishes to provide a continuity of care from pre-flight training to in-flight mission and during our post-flight recovery. And we're doing this all powered by the only multi-omics human space flight data set in existence today. And this matters because in deep space, we need to provide personalized, targeted medical care. Precision medicine and pharmacogenomics is going to allow us to enhance crew health and performance, thereby ensuring mission success. Precision health is going to allow us to shorten recovery time, which leads to executable landing missions and the future of colonization. But ultimately, this is about safety. We're flying humans in space with medical conditions that have never been flown before, and we're going out further and staying there longer than we have in decades. Our team has literally written the book on space genetics. My co-founder, Chris Mason, wrote the book on the next 500 years. He is also the lead author on the NASA twin study and the most recently published SOMA package. Elia Overby, equally lead author on the SOMA package and is leading the way on the commercial space genetics program. Matt McKay is doing commercial precision products on the market today. And my career has been spent in translational healthcare, taking in silico discovery and moving it right into product. So we are primed to do this work, but we don't want to do it alone. Space is big. And our parent company, BioAstra, is a nonprofit specifically designed to work with the global community to solve these really hard problems. We are thrilled to work with the Humans in Space cohort, and we have a number of avenues which we can do so, from our research program, which is always looking for collaborators, mentors, and fellows, to highlighting the work of this crew, of this cohort on our podcast. But Precision Payloads, listening to everyone talk today, shows us just how important our pipeline is for bringing new therapeutics directly into practice. We are in our pre-seed now, hello, which means we are prototyping our packaging and refining our pharmacogenomic pipeline, and we have a target to fly our product on a mission within 1 year. As we move into our seed round, we will be closing B2B sales with launch providers and securing government contracts. But we know space is not at scale yet. We have to provide a terrestrial product line. And so that is what we will be exploring in our next round. We know the target market space, we love space, but there are only 2 companies flying humans today, and only one of them has a working spaceship. So we have to get to the next level, which brings us to the terrestrial marketplace. We have secured a partnership with a facial plastic surgery practice in Beverly Hills, and we believe that we can take the inflammation reduction from space and apply it directly to post-recovery care packs on Earth. In short, we are space genetic experts building precision medicine technology and putting it into packs for our astronauts, for our crews, for their training, for their mission success, and then when they return on Earth for their recovery. And we're doing this in luxury packaging with the most advanced biotech solutions available on the market today. Thank you.
Thank you very much, Savvy, for that wonderful pitch. Now we will move on to the Q&A session. We'll just move through the slides. Yes, Dr. Ken Savin, please feel free to share your question.
Can you give us some examples of what you're putting in the packs?
So the easiest example that we can do today is there's only one supplement that's flying in space, and that's vitamin D, which is when we consider nutritional deficiencies and a number of other there are a number of other things that we can fly. We can fly, something as simple as melatonin or something as simple as magnesium, and we can improve a number of different health conditions in space. But ultimately, we're looking for the markers for reduced inflammation and reducing the IL-6 line targets.
Thank you very much for that question. Yes, Dr. Patrick Hollis.
Hello, thank you for the presentation. I would like to follow up on Ken's question that let's say that it turns out that the best precision medicines for space are more like injectables or more like complex biotech and gene therapies. Have you done a risk assessment? How would you go to that? How would you package that? And are you in that game also or not?
Yeah, believe it or not, I mean, I think it's such a great question, and I just don't think we're there yet. The medical packs that are flying today are camping bags, nylon camping bags with Velcro and Ziploc bags attached. So the steps that we have to get to from that level of technology all the way to advanced injectables and new methods of treatment is actually quite big. So that is something that should be on our pipeline, and we will explore it as we progress as a company.
Thank you. Yes, Stephanie.
Thank you for that presentation. Are you manufacturing all of the different drugs and medicines that are going in the pack, or are you just
No,
gathering
no.
together,
We're
putting
just
them in the bag?
we're putting them together. I think, and that's the strength I think that we have in the Humans in Space Consortia, is that we can create this pipeline to do the clinical research trials that are maybe needed in space, and to actually put that in a packaging that would make sense and be part of the whole ecosystem of clinical care in space.
Got it. Thanks.
Yeah.
Thank you very much. Due to time constraint, I think Kevin's question would be the last one we'll be able to take.
Okay, thank you. Good morning. Super presentation. My question is, are you focused primarily on prophylactic solutions or therapeutic solutions? And if it's the second, how are you going to solve the diagnostic challenges that currently exist in space?
Yeah, I think it's such a great question. Initially, I think we have to be more prophylactic, but we do care very, very much about the acute care and the mediated medical care. So working with partners who are building diagnostic technology, point of care diagnostics is absolutely critical. That would be something that we really care about. And we've done some work on our side to perfect point of care omics sequencing in space, but like actually taking that to the next level of providing like diagnostic care is critical.
Right. Thank you very much. Thank you, Kevin, and thank you, Savvy, for joining us today. I think it was a very insightful Q&A session. All right. So before we continue on to the next set of presentations, we're going to take around 3-minute break. So judges, please feel free to turn off your camera, have some water break. But while we do the break time, we're going to show on the screen a short clip about humans in space and what we aim to do through this program. So please enjoy, and we'll see you again in 3 minutes. Thank you.
Humanity has been a history of endless exploration. Over the decades, we have continued to explore deep in space, far beyond where we are born. People still might ask, what is there in space? Can we live without gravity? Can everyone go to space one day? Can there ever be a second Earth? But while paving the path to find these answers, extraordinary pioneers ask questions in a different way. Can sick people go to space? Can we utilize space environments to enable permanent habitation? Can we enable our children to explore beyond their wildest dreams? These extraordinary questions will transform our everyday existence. It's not for the extraordinary. It's the extraordinary for the ordinary. Now, it's time to reveal the answers. For humans in space.
We will now we'll resume the virtual pitch day in few seconds. Judges, if you're here, please turn on your camera and we begin the session in few seconds. Right. So the next part of today's pitch session, we're going to listen from one equity investment presenter and then followed by orbital launch funding applicants or those teams with in-space experiment plans. So for the, I guess, second to the last equity presenter for today, we have BioConnect. BioConnect is a startup based in South Korea that specializes in developing healthcare management solutions based on non-contact biosignal collection technology. Please welcome to the stage Yeonjun Kim, the CEO and founder of BioConnect. Yeonjun, please feel free to share your pitch with us.
Nice to meet you, everyone. I'm Yeonjun Kim, the CEO of BioConnect. BioConnect it has a non-contact biometric analysis technology based on AI vision. We believe our technology is needed in space. BioConnect was founded in 2018. We have a technology to measure heart rates, variabilities, oxygen saturations, blood pressure using remote water processing graph. We have supplied our technology to broadcasting companies, pharmaceutical companies, construction companies, and healthcare service companies. Let's talk about the market problem we see. In isolated environments such as space, continuous measurements of biometric is particularly important. However, off-the-shelf instruments are difficult to use and unsuitable for the space environments. On Earth, there are some constraints to the biometric measurement environments for disabled and elderly individuals. Let me explain why it is suitable for space environments. One, it can analyze 5 biometric simultaneously at time with a common camera. 2, convenient to measure by looking at the camera without attachments. 3, continuous measurements allow users to prepare for emergencies and monitor their health. We are working in partnership with many companies based on scientific evidence and patents. We aim to contribute to the health of astronauts by applying our technology to health monitoring in the space environment.
태국의 서돔 카이트 환자나
We are proven one team of healthcare experts to the co-founder work at the same company. As a team, we are passionate about making a meaningful impact on human health, especially in the unique environments of space exploration. HIS court studies provide an opportunity to validate the accuracy of the technology and provide clinical evidence for medical device approval. It also enables research such as glucose level and dementia using deep learning. Our company has 2 main areas of focus in space. The first is to provide a solution to monitor astronaut health in real time to prevent emergencies such as cardiac arrest. We also plan to accumulate biometric data on the effects of drug taken in space and provide its pharmaceutical companies to help them develop new drugs. We have 4 main business models on Earth. The first is a sale of hardware with software, install kiosk and smart mirrors in public areas. The second business model is supply medical device to hospital, to health center. The third business model is provide SDK to telemedicine service or healthcare services. Four is analytic data platform services. The target market is the public healthcare services market for local senior center, workplace, senior town, and registered healthcare. We are setting up experience zone in the public area for the elderly and disabled to test the products. BioCorrect's unique value proposition is real-time, non-contact, multi-biometric measurements, low cost, and no additional devices. In the second quarter of 2026, we intend to submit as a medical device and extend its application to the medical fields. In space, we will conduct in scale of a study such as diabetes and dementia. Finally, by 2028, medical device revenue will drive growth. By 2029, we expect to generate $5,000 billion in revenue from Vital Tracker. Thank you.
Thank you very much, Hyunjin Kim, for that pitch. We will now move on to the Q&A session. Judges, if you have any questions, please raise your hand and I will assist you into the session. There are no questions. Yes, Patrick.
Yeah, you showed quite a bit of milestones. It looks like a lot of ongoing work, but not so big team. I was wondering if it was the full team or your company is actually bigger, and are there some more primary focus areas, especially when it comes to space? Is there like a high focus area that, okay, this is the first sort of risk that we want to prevent with our monitoring? What would be the first use case in space risk analysis, or just getting it there and collecting baseline data for validity?
Our company addressed the critical challenge of preventing cardiac arrest in astronauts and ensuring real-time warnings, health change in space. Gravity's influence in blood pressures and heart variabilities, and current medical devices in critical. Our technology enables real-time monitoring of multiple biometric indicator without attachments, providing early detection of multiple biometric indicator. Without attachments.
Right, thank you very much. Yes, Israel.
Hey, thank you very much. Great presentation. Can you say a little bit more about the actual monitoring? Is it just by AI of monitoring the face, or what's the technology?
Yeah. Our technology is RPPC. RPPC is a remote PPC technology. In use the computer vision technologies to detect change of skin color by photographing the blood vessel on the face with a regular camera, such as a webcam. The change in skin color are converted into the frequencies to obtain pulse wave. We applied this pulse wave to an algorithm we developed to obtain biometric informations.
Thank you very much, Israel. Right, so I believe that was the last question for this session. Thank you, Hyunjin Kim, again for that wonderful pitch.
Thank you very much.
Thank you. Now we will move on to the Orbital launch funding applicants. So these teams will be presenting also their plans for in-space experiment. And for the first team, we have Lunar Medical Incorporation. So the Lunar Medical Incorporation is an early stage startup based in Canada that develops medical and life support systems for lunar exploration. So please welcome to the stage David Musson, the CEO and founder of Lunar Medical Corporation. David, feel free to start off with your pitch.
Thank you, Betty. Good morning, good afternoon, everyone. Hello from Canada. My name is David Musson, as Betty introduced me. I am the co-founder and CEO of Lunar Medical. Lunar Medical is a Canadian technology company that was founded to solve the challenges of medical care delivery in spaceflight. And so in a nutshell, what are we doing? We're trying to redesign healthcare delivery for the space age. And we've developed an integrated, intelligent monitoring and AI decision support platform, which I look forward to telling you about. If we talk about it in terms of problem and solution, my background, we'll get into backgrounds in a while, but I was a flight surgeon in the Air Force for many years, which is similar to space flight in terms of medical care. We select the fittest of the fittest. We disqualify people who have medical conditions. And for space flight, if somebody gets really ill, we just bring them back to Earth as fast as we can. We're entering an era that a lot of us are calling new space. We're looking at citizen astronauts, but these future flyers will have medical conditions. There are limited options for early return from destinations like the moon, and early return is virtually impossible for projected Mars missions. And we're entering an era where medical events have to be managed on board in situ. And so in a quick summary, the old model for space healthcare support will not work for new space. We've developed the medical care and communication integrator, which we call McCoy. It is an integrated digital health suite. You can see a picture there. It is sitting currently at the Canadian Space Agency, used for demonstrations and testing. It provides device agnostic and manufacturer agnostic sensor integration. It does analysis, provides AI guided decision support. It's really built along a model of autonomous care down the road. And it's capable of machine learning, and it provides both advanced telemedicine support and just-in-time training linked to the assessment of the condition at hand. The impact of this work, we see a commercial space station immediate impact, but we see it also to Moon, Mars, and beyond. In the commercial sector, we want to enable everyone to fly, which I think has implications for commercial spaceflight, but it's really what everyone wants to do. For the Moon and Mars, we're looking at providing medical care infrastructure, and our big driver really is improving terrestrial care. We have many areas in Canada, many northern communities that have minimal medical care, rely heavily on telemedicine. We have a lack of physicians, a lack of advanced nurse practitioners. So we're trying to solve these problems. The team, I won't go into details, but the team has extensive expertise in operational medicine in remote and austere environments, space medical support. We've deployed medical simulation to a number of areas. We've worked heavily in body-worn and ambient sensors. We have deep machine learning and AI expertise on the team. We've even looked at things like psychology in extreme environments like the Antarctic. You see some pictures here, but yeah, we've looked at crew selection, telemedicine models, remote ultrasound, diagnostic systems, and we've deployed to areas like Hot and Mars Project and Eureka Weather Station in the Canadian Arctic, Mauna Kea, and a lot of laboratory work. Spaceflight is a team sport. We are focusing primarily on digital signal integration, AI decision support, machine learning. We are, as I said, manufacturer agnostic for the sensors. So when I look at like the previous presentation from BioConnect, that's the kind of technology we would love to integrate in our systems. And for this opportunity, we're looking for really orbital technology tech demonstration on orbit. All the different functions that you see there, we'd like to run those through, and at the same time, piggyback on some machine learning AI science on operator recognition and performance changes. Our current status, as I said, our device is sitting in the Canadian Space Agency right now, so we do have a prototype. It's being well received. We have a certainly work plan for the next 12 months. We have applied for and are waiting for the next tranche of Canadian Space Agency funding. We were well funded for the original prototype at $2 million Canadian. The next round is for further development of our platform and porting it onto an ISS-friendly system, which we don't see as a major challenge. And you can see the experimental timeline there with the sort of standard pre-flight work to get us to launch in about 18 months. And with that, I'm going to go to my last slide and just say we're looking to try and change the way healthcare is delivered in space. We see an opportunity to work with many of the other presenters in the HIS challenge. So that's very exciting, and happy to take any questions. We want to do this, help us get there. Thank you.
Thank you very much, David. We'll now move on to the Q&A session. Yes, Dr. Ken Savin.
Is the solution a telemedicine or a machine learning AI approach, or is it a mix of the two?
Excellent question, and it's hard to explain it all in 5 minutes, as you might imagine. It's really designed as a standalone, internet-independent clinical health suite that provides AI and decision support. The historical model for spaceflight obviously has been very heavily reliant on telemedicine, and for a terrestrial model, telemedicine will always be a key. So telemedicine is a capability of this system, but its primary function is on-site monitoring, on-site decision support, on-site data collection, application of machine learned models, and refinement of those models in situ, if possible. Obviously, in space, there's a limited ability to send huge amounts of data back to Earth. So if you can't do in situ machine learning, that poses challenges. So that's its fundamental purpose, I would say.
Thank you for that question. Yes, Stephanie.
Thank you, David. And that was my original question. So I will ask another question instead, which is the picture that you showed had a lot of different machines hooked up to the prototype. And I'm curious, when you say that you want to test this in orbit, is everything already there on the ISS that you need, or would you need additional machines or whatever it might look like in order to do a true proper test?
Yeah, excellent question, because it looks terrifying. It looks like we're trying to launch 3 tons of hardware into orbit. What we built, the space agency asked us to build a prototype for them. We retained the IP, but we actually built them a simulator. So we built them essentially a functional orbital simulator. We've done some previous work with that at Harvard, actually with collaborators, actually with the previous winner of the Humans in Space Challenge. So we gave them essentially a mock-up, but at the core of that is a software system that does device data integration. It applies expert systems and machine learned models, and it stores data. So yeah, we're being asked to fly it on a Surface Pro laptop, which has limited computing power, but we think we can do it. Ideally, we'd like to fly a server and a bag of sensors, because we don't build sensors. We like to use other people's sensors. We will take advantage of what other sensors already exist on the ISS. They'll certainly have pulse oximeters and other devices, so we wouldn't want to fly redundant equipment. But we're very, very interested in the non-contact sensing, whether it's physiologic, like BioConnect was just presenting, or behavioral. I'm a flight surgeon, but also applied psychologist. So I would love to do behavioral monitoring of the system. So we're trying to build the core of this system and let others build the sensors.
All right, thank you very much. We'll have the last question from Cesar.
Yes, if you can quickly elaborate on how you want to do on-ground validation of your solution before going to flight.
Right, so the validation covers, and we're almost out of time, but it covers obviously everything from sensor connectivity to storing and retrieving data, doing some machine learning, probably all in a laboratory session, because the ground analogs don't really replicate the things that we need to look at for ISS. And then the sort of FDA and Health Canada certification, obviously a very different story with clinical experience, but primarily usability and connectivity.
Thank you.
Thank you.
Perfect. I think it was a very interesting questions that came out during this session. Thank you again, David, for joining us today.
Thank you, everyone.
All right. Now, moving on to the second startup for the orbital launch funding model, we're going to invite to the stage Mylin H. Mylin H is a startup founded in United Kingdom that specializes in developing remote monitoring and personalized rehabilitation software for neurological disorder. Please welcome to the stage Ziad Tayeb, the CEO and co-founder of Mylin H.
Super. Hello, this is Yet, and I'm here today to present our company, Mine and H. It all started for me after my mother was late stage diagnosed with multiple sclerosis, a devastating brain disease, and regrettably, she didn't receive proper treatments. There were no solutions to monitor her disease progression or rehabilitate her. And sadly, she ended up being fully disabled and unable to walk anymore. So that clicked with me in a way that I decided to pursue a PhD in neurotechnology in the big hope that I'd have my mum regain mobility or at least better manage her disease. Right after the PhD, my co-founder and I decided to roll up our sleeves and start Mine H, whose grand mission is not just to revolutionize brain health monitoring or rehabilitation here on Earth, but more notably, we are on a mission to transform brain health in space. Now, beyond my personal story, it's not working there. Okay, so beyond my personal story, it turns out that 1 in 3 astronauts experiences memory issues and cognitive deficits in terms of visual processing, speed, and attention. And they took up to 3 years for full recovery. And this is primarily due to radiation, microgravity, weightlessness, and more importantly, mission-related stress. And unfortunately, this raises and increases operational health costs before, during, and after space missions. It's like a bit slow to move this. So in terms of the technology, what we've created, what we call a multimodal brain-machine interface platform that combines our proprietary machine learning, whose name is neuromorphic computing, with cognitive games to monitor and improve brain health remotely. So the idea is you basically play different games. Those games, they will stimulate your brain in different ways, and then we capture a plethora of data as you interact with those games, whether it's your EEG, EMG, speech, mood, motor data, gait, whatever that may be. And then we basically use our proprietary machine learning to translate that data into sorts of digital biomarkers to monitor visual processing, speed, attention, memory, dexterity, and would thereby inform the physician about treatment effectiveness, treatment effectiveness and disease progression. More importantly, we don't just park it there. We use the concept of neuroplasticity and rewiring the brain so that we create a bespoke game-based treatment plan whose purpose is to enhance cognitive abilities. Beyond Earth, the idea is to leverage the same technology to monitor and rehabilitate astronauts before, during, and after space missions. In terms of the team, it's me. I hold a PhD in neurotechnology. I'm also an associate professor of brain-machine interfaces, presumably the youngest in the UK. My co-founder holds 2 master's degrees, one of them in space. We've got a chief clinical officer who's got 25 years of experience as far as brain health is concerned, and our marketer used to work for Neuralink and Paradromics. We also have really strong advisory board members, including Lynette Hunt, who used to be the director of the Singapore Space Agency, or they call it association. Some of our partners include Stanford Medicine, the University of Cambridge in the UK, UC San Diego Health, NYU. Some of our investors include Boryong, the government of Luxembourg, and a couple of other investors. In terms, as far as the experiment is concerned, so the idea is basically to demonstrate the feasibility of monitoring brain and body changes during space flights using a novel concept, which is some sort of visor-like sensor, cognitive games, and neuromorphic software, which is some sort of biologically inspired machine learning. So we're going to establish a baseline, use the device for cognitive monitoring prior to embarking on that space mission. Thereafter, we'll be remotely kind of monitoring the astronaut during the space mission, and then look at the what we call neuro recovery or rehabilitation post space flight. And the idea is basically the value proposition is to enhance cognitive performance of those astronauts prior to embarking on that space mission, ensuring healthier astronauts, and accelerates neuro recovery, which would thereby reduce mission costs and increase its efficiency. Where are we on this journey? So, like a young company, but we've been able to test this with multiple patients. We're on the cusp of commencing an international clinical trial with 350 patients. We've got some of the best hospitals on board. We've received around 2 million in non-dilutive money, around $1 million raised from equity, from private investors. And as far as the space sector is concerned, We've been able to, we won the NASA iTech Awards in 2019, the Karen Space in 2022, and we have started a collaboration with Virgin Galactic.
All right. Thank you very much, Ziad. We will now move on to the Q&A part of the session. Just quickly move through the slides.
So, yes, like it's been a bit slow, but it's fine. Yeah.
Yes. Can we now shift to the Q&A? Yes, we will now move on to the Q&A part. Yes, Patrick, please feel free to ask your question.
Well, thank you for the great pitch. I was wondering, you mentioned that you have a 350 patient clinical trial. Is that just testing the MVP, the hardware setup, or is there some games already ready for some indications and that you would like to test it also in space, or the space is only about just testing the hardware and the setup?
No, the space is a brilliant question. So first and foremost, just make this unmistakably clear, the space will be testing the whole system, which is a combination of software, hardware. When I talk about the software, I talk about the games, because that's basically the proprietary, kind of the most important thing is how to gamify neuroscience so that you basically enhance cognitive abilities. Also to try the same thing that the hardware is already certified, and we're now looking to basically certify, get the FDA approval when it comes to the games and the machine learning to interpret the data.
Yeah, and just to quickly follow up, these clinical partners that you have, they are more like focusing on the games and looking at what would be the first sort of game asset that treats some condition.
Yeah, so
already some leads in that sense.
Yeah, exactly. So that's basically the purpose, is to demonstrate kind of rehabilitation improvements after playing certain games, and more important, to monitor those patients remotely as well.
Thank you very much for that question. Yes, Dr. Paul Camus.
Yes, hello. Thank you very much for this great presentation again. Do you use mostly software, and in terms of hardware, standard data, I would say data management technology, or do you have any specific advanced sensor related to brain detection, whatever, in your panoply of sensors?
Yeah, we do. We do have some sort of visor-like sensor to capture what we call EEG, which is non-invasive brain data, and that's proprietary. We don't just capture EEG, we also capture EMG from the muscles, gait, and body movement. So like every time you move, and then the software basically takes all the data, processes that, and then transforms that into sort of digital biomarkers. Does that answer the question, or am I?
No, it's okay. Thanks a lot.
Thank you. Appreciate that, man.
Thank you very much, Paul. Yes, Martina.
Can you please comment on how time-consuming this will be for the astronauts? You are talking in the presentation, you have some like 15 minutes, 20 minutes. So how long and how frequently?
Okay. So the answer is not one size fits all. So it all depends on that kind of baseline establishment process. The idea is you would basically, prior to embarking on that space mission, you'd play all the games. It's going to take 20, 25 minutes. And then based on that, we'll basically understand whether you've got some visual processing, speed issues, whatever attention, then we'll personalize that idea. Usually the experiments for playing the games is not going to take more than 10 minutes because 25 minutes is when you play like 20 different games, which is all the games we've developed so far. And then in terms of like getting the sensor and everything, it takes less than a minute. So I would say the entire thing is perhaps like 12 minutes. In terms of the frequency of that, again, it has to be personalized, but I would say you would do it like once a day or so.
Thank you very much for that great question. Thank you, Ziad, for joining us today. And, I think it was a wonderful pitch.
Thank you.
Right. So the next presenter is a researcher under the Orbital launch funding. First up, we have Devin Lundin from Memorial Sloan Kettering Cancer Center. He will be presenting his research proposal on preventative measures against DNA mutation caused by cosmic radiation. Devin, please feel free to take on the stage.
Hi, how are you? I'm Dr. Devin Lundeen from Memorial Sloan Kettering. Very excited to tell you about our work today. We're researchers in DNA repair, and we are working on ways to modulate the DNA repair system in humans to shield astronauts from cancer. And so the main fundamental problem that we're trying to address is that cosmic radiation is increasing astronaut cancer risk and limiting our ability to explore space. So as a way to orient you, the NASA astronaut career dose limit is currently set at 600 millisieverts. You and I, sitting in whatever room you're currently watching this in, over the course of 12 months, will get 6 millisieverts of background radiation. A trip to Axiom Station in 2030 will net you about 20 times that if you stay for a year, and eventually Lunar Gateway will be much more than that. And a trip to Mars, which is a minimum of 21 months, is even higher and essentially uses up your entire dose limit. And a big reason why that dose limit exists is that this radiation causes a lot of DNA damage and increases your cancer risk. We're modulating a particular type of DNA repair called alternative end joining, which is driven by a protein called polymerase theta. And so our fundamental research question is, if we block polymerase theta, can we reduce cancer risk? And without getting too mechanistic, polymerase theta actually introduces mutations back into the genome when hit with cosmic rays. So we have this very simple thesis statement: cosmic rays plus polymerase theta equals high cancer risk, and cosmic rays minus polymerase theta results in a reduced cancer risk. And we're looking at a clinically relevant drug called ART-558, which is a very strong inhibitor, reversible inhibitor of polymerase theta. We're very proud winners of the 2023 Humans in Space Research Award, and we've been using that money actively to perform ground studies that include work at the Columbia Neutron Beam Facility, a linear particle accelerator, where we take TK6 lymphoblast cells. Some of them are inhibited, polymerase theta inhibited, others are left untreated, and we hit them with radiation. And the readout of that is cell survival, chromosome structure, and whole genome sequencing to see if the drug works. We've already made some great advancements in preliminary data in terms of cell survival that you can see on the bottom left-hand corner. Each of those dots are cell colonies, and you can see that those colonies die off with radiation. And we have been looking at individual chromosomes of DNA with a partner company, Chromatid, to get these beautiful images of individual chromosomes where we can count mutations to see if the drug is working. So our orbital proposal is essentially to run the same experiment in space, and we've been working with Odyssey Spaceworks, last year's HIS winner as well, to develop a CubeSat incubator with off-the-shelf components, and essentially run the same experiment with TK6 lymphoblast cells and measure cell survival, have a live cell damage sensor, and perform some whole genome sequencing as well. We're hoping that the planned uptime would be about 30 days. This incubator functions in physiological conditions, and there will be cameras on board to essentially monitor both in bright light and fluorescent for our damage sensor to be able to tell how the cells are doing. Every couple of hours, we're able to do data downlink and really analyze in pseudo real time what's going on with the cells in orbit while we have our satellites up there. We have made a lot of progress on our roadmap, so we are set to go back to the particle accelerator September 12th and continue our data optimization under the simulated radiation conditions and have this baseline validation of this theory. And we're continuing over the next year to finalize the design of our genomic damage sensor and complete our customized hardware with Odyssey Spaceworks. And overall, this is really planned for the Artemis missions. Of course, it will be beneficial to Axiom, but Lunar Gateway would be fantastic as well to protect against radiation in this way. Overall, the design is implemented to determine if polymerase theta inhibition reduces cancer risk following this exposure to cosmic radiation. We would love to use this methodology to assess additional drugs. This drug we feel quite confident about, but we will test other drugs in the future. And we can expand to animal studies on Earth, eventually this Axiom Station, hopefully the moon. And all of this functions to broaden our understanding of DNA repair. The team is based out of Memorial Sloan Kettering, led by myself and Dr. Daniel Higginson, a radiation oncologist. We've got funding from the NIH and Bohr Young, as well as some critical assets with the Columbia neutron beam, Odyssey Spaceworks, Chromatid, access to Sloan Kettering itself, and we're hoping to launch at the end of 2025. So thank you very much.
Thank you, Devin, for that pitch. We will now move on to the Q&A part. Yes, Patrick, please feel free to ask your question.
Hi, Devin. Thank you for the very clear presentation. I have two questions. Is this how much this inhibitor is characterized? Is it interfering with any other standard DNA function? And on the long run, what would you see? What would be the delivery? How much switch and off during maybe solar storm? Is it just like higher dose, or how do you modulate? And would be their pharma partner to commercialize this?
Yeah, great questions. So the clinical relevance of the drug is under human testing right now. It's in clinical trials. And there are other compounds that sort of do this as well it's very clinically active right now. There's a lot of interest in polymerase theta inhibition for cancer treatments on Earth. It's an interesting question. How do you would you change the dosing for solar radiation or solar storms? I'm not sure what the answer to that would be. I think we're optimistic that this is a standalone treatment for galactic cosmic rays, maybe more than solar radiation, and that shielding and mission planning might be a more appropriate countermeasure for solar radiation. But we'll see. Maybe it can be used in conjunction. We need to do some more testing.
Excellent.
Thank you very much, Patrick. Yes, Kevin.
Hey, good morning. I'd like to echo the sentiments. Great presentation. Apologize for the video. I'm having technical challenges. Two questions. One, on your orbital experiment, are you intending to return your cells for sequencing, or are you just going to try to get as much you can on orbit and let the deorbit happen?
Yeah, we would love to do sample return. I think that might still be a couple of years off. So in terms of our milestones, I don't think we're going to be able to do sample return based on our schedule. But we're going to try to do what we can on orbit and try to do some technology development to see kind of what we can do with that. And then we'll see. We're intending this to be a platform to continue to test additional drugs, and we would love to get down mass at some point. And I think that Odyssey and others are working on that capability.
Okay, great. Yeah, second question. So your drug, is it just a straight up molecule, or is it more CRISPR based on working on editing?
Yeah, it's a drug. We intend for it to be reversible. I think an irreversible gene editing is not yet in the cards. That might be a little too risky, but maybe in the future we'll have some genetic modification for spaceflight for humans. But right now, a reversible inhibitor.
Okay, great. Thank you.
Thank you very much. We will take the last question from Israel.
Thank you. Hey, Devon, great presentation. Just maybe to follow up on the last question. So the idea is to develop a system to test the radiation effect on gene editing, or just select specific drugs and test it.
Yeah, so it's specific drugs. So right now, there are no known radiation countermeasures for cosmic radiation, and so both in terms of testing drugs and the platform itself, both are quite novel ideas and are necessary. I think one of NASA's 5 spaceflight hazards includes space radiation. And if we want to go to the moon and Mars, something has to be done about this. And so we're developing kind of both a practical solution as well as a platform for continued testing, we feel.
Thanks.
Thank you.
Thank you very much for that question. Thank you, Devin, for joining us today. I think it was a very good presentation.
Thank you.
Right. So before we move on to the last 4 presenters for today, we'll have another short break. So we'll have a 3-minute break so everyone can have some water break and restroom break, and we'll be coming back to hear the last 4 presentation. And during the break, we'll be playing a short video.
We moved from carrying space to humans in space. Our mission and our vision is having more people up in space and allowing them and providing infrastructures.
I was thrilled to be invited back for a second year. Seeing companies and ideas begin to think about how humans can thrive in space, not just survive in space.
Hi everyone. We'll be restarting the virtual pitch day in a few seconds. If you're ready, feel free to turn on your camera and stay with us. All right, so the next set of presenters are researchers applying for the Orbital launch funding track. And I'm really truly excited to hear their research proposal for experimentation in space. First up, we have Helene Park. So please welcome to the stage Helene Park, researcher from Inha University. Her research leverages space environment and cultures cardiac cell in microgravity to solve or study molecular pathophysiology of atrial fibrillation. So, Helene, if you're ready, feel free to take on the stage.
Yeah. Thank you for your kind introduction. It's a privilege to present my research at Humans in Space today. I will briefly discuss our work that addresses significant challenges on Earth, particularly in disease diagnostic modeling. In specific, we are going to investigate the identification of optimized cardiovascular disease treatment by regulating the expression of aquaporin channels using space environment stimulation. In specific, we are going to investigate the presentation will cover the following topics. cardiovascular disease remains a leading cause of mortality worldwide, with its incidence rising rapidly. Despite advances in medical science, achieving a fundamental cure is still challenging. Therefore, there is considerable need to develop, innovate, and effective therapies based on novel mechanisms. Space environmental stimuli have been shown to produce unique effects not seen on Earth. However, unlike previous study, our study is the first to utilize space environmental stimuli for human health improvement. Thus, our goal is to identify the close correlation between space environmental stimuli and genetic factors and to develop candidate drug for the disease by modulating target signaling. The expected outcomes of our project, including the development of biomaterial with therapeutic applications, are not only scientifically significant, but also economically crucial. This advancement paved the way for new diagnostic methods profoundly impacting the healthcare industry. Additionally, in space, our findings contribute to the development of new treatment protocols and options for astronauts. In terms of research capabilities, I have been leading national research projects focusing on developing therapeutic strategies using integrate RNA genome data from human cardiac tissues. Our research center has a hypergravity clinostat, pressure chamber, and space radiation equipment for creating the optimal and suitable space environment. And there are telemetry system and PET clamp for cardiac research as well. Also, we have an international patent on the treatment of atrial fibrillation with an aquaporin inhibitor related to this project. The overarching objective of our study is to identify and validate optimized treatment candidates for cardiovascular disease using the unique conditions provided by space environmental stimulation. When looking into the result of our previous research, the left panel shows the effect of changes in gravity, and the right panel represents the result of identifying the effect of changes in pressure on atrial fibrillation treatment. Recently, we have identified and confirmed changes in aquaporin channels in vitro and in vivo atrial fibrillation models closely related to space project and have registered in international patent. Building on this finding, after finding target gene for cardiovascular disease through ground research, we plan to conduct orbital experiments to confirm their effectiveness. As the last section of this presentation, the experiment milestones are as follows. The part in milestone 1 has been progressed, so it seems possible to shorten the research period. After milestone 3, patent application and technology transfers are planned. This concludes my presentation. Thank you for your attention and for the opportunity to share our research today.
Thank you, Helen Park, for that wonderful pitch. We will now move on to the Q&A part. Judges, if you have any questions, feel free to raise your hand. Yes, Dr. Ken Savin.
So it sounded like you are going to try to generate both systems that allow you to test molecules, but also you're going to be generating your own molecules. Are you creating your own new molecular entities for treatment?
Atrial fibrillation occurred due to changes in ion channel, including cardiac fibrosis, inflammatory response, and calcium regulating protein. But ion channel regulating drugs are not very effective, do not effectively prevent the progression of the disease and have many side effects on other organs. Accordingly, the need for drug development targeting new mechanism has increased.
Thank you very much for that question. If there are no follow-up question, there's a question from the Humans in Space team. It is our understanding that your experiment requires astronauts to involves the precise handling of cells during the in-space experiment. So, are there specific challenges that you anticipate astronauts may face while conducting this task? Yes, to clarify our question, are there any specific risks that you foresee when you're conducting an experiment in space?
We synthesize candidate aquaporin for SRRNAs and determined by examining their efficiency in suppressing target gene expression based on PCR and Western analysis.
Right, I guess that's the end for the Q&A session. Thank you very much, Helen Park, and thank you, judges, for joining us again. And we will now move on to the next presentation. The next presentation will be coming from Jang-Geun Kim from Weill Cornell Medicine. He will share his research proposal on studying how the roles of individual genes change in microgravity by establishing a gene perturbation dictionary. So please welcome him to the stage. Jang-Geun Kim, please feel free to share your pitch when you're ready.
Yeah, thanks for the introduction. Today, I will present the single-cell space perturbation dictionary in orbit. It has been known that spaceflight changes the gene expression network, and the genetic network change underlies the spaceflight-associated biological risk. Due to the complex nature of the genetic network, so far it is hard to understand the role of each gene in the context of spaceflight. Here, I propose to provide a space gene dictionary, which explains each gene's behavior in space and its effect on the genetic network to aid future research and medicine. The function and interaction of genes are the underlying building blocks of the critical space healthcare risk suggested by the Human in Space Challenge. However, so far, there is no space gene dictionary that can be utilized for understanding and disentangling the changes. Our team has worked on space omics project for over 10 years, including NASA Twins study, SpaceX Inspiration 4 Polaris Dawn Axiom, Blue Origin, and NASA missions. We were able to find the spaceflight-associated transcriptomic changes. However, all transcriptomic studies gave us a correlational output. It is noted that correlation is not causation. So still, we can't say the role of each gene in space, which gene sets are directly affected by spaceflight. To solve this problem, it is essential to perturb each gene to identify its roles in space. We suggest utilizing the latest CRISPR gene modulation system, single-cell technologies, and computational algorithms to solve this problem. Briefly, single-cell technologies enable transcriptomic profiling of heterogeneous population, and CRISPR technologies enabled multiplexed perturbation. By integrating these tools, single-cell multiplexed perturbation profiling is enabled. With this approach, we'll provide a database and tools to disentangle the lol gene in space. Specifically, we'll provide the space gene perturbation dictionary, which can be used to encode the foundation model and decode existing and upcoming data sets. Also, this approach is cost-effective. Multiplexing a high-throughput method is more affordable than classical perturbation-Burke transcriptomic analysis. Here are our core team members. Dr. Mason and I have worked on multiple astronaut multiomics studies. We have Dr. Satija Lab in our team who has pioneered the single-cell and perturbation sequencing field. Also, we have Waynomics team, which has expertise in developing microfluidic biospecimen cartridges for long-term automated cell culture in space. Our space gene dictionary has great potential to make synergy with human in space cohort, which can be utilized in many types of molecular, cellular, and physiological projects to interpret the data and identify drug targets and other kinds of synergies described here. Here is the experimental detail. At the top left, we have human cell lines expressing CRISPR-I, which inhibits specific gene expression. We designed biological pathway relevant to spaceflight, including immune pathways, radiation pathways, microgravity pathway, and spaceflight conserved pathway. At the bottom left side, we'll make a cell pool optimized for perturbing spaceflight relevant pathways. Then we will send the cells into orbit and space analog environment that analyze the data. At the top right, in parallel, we are developing an automated long-term cell culture device optimized for the space environment. Our team has worked on several major space biology projects featured in Science, Cell, and Nature. Satija Lab has expertise in perturb-seq, and Waynomics team has expertise in microfluid biospecimen cartridge development for use in space. So far, we have already prepared cellular and computational tools. Still, we need to develop more on the MVC unit and test our perturb-seq system with the MVC unit on Earth and space analogs and get flight approval and eventually send the cells in space with the automated cell culture system. And here is the expected timeline. We have several resources, representatively World Quant, Walton Medicine, and NASA SBIL Phase 2 Fund. Expected milestone would be the automated MVC Space Gene Dictionary database, Space Pathway Perturbation Library, biobank patent and license, and we'll further expand this in vivo organoid and drug. And here are some revenue generation ideas. Thanks for listening, and happy to take any question.
Thank you, Jang and Kim, for that pitch. We will now move on to the Q&A part. Judges, if you have any questions, please feel free to raise your hand. Yes, Dr. Israel Biran.
Hey, great, very interesting project. So my question is, what's the most difficult or the most resource that you need for this project? Is it develop the actual system, the single cell system, or the molecular system? What's your view on that?
Yeah, thanks for the questions. Basically, the system has been, most of the cellular and computational system has been validated on Earth with a previous Satija Lab paper, but we need to adapt some pathway for spaceflight, but it's not that technically difficult. But the kind of huddle would be, we are developing our own molecular, the cell cartridge device. So we need to optimize the cartridge device for long-term cell culture adapted in space. And also we need to find some opportunity to actually send the cells to the space.
Thanks.
Thank you very much for that question. Yes, Martina?
Can you please elaborate on your involvement in crewed space missions such as Inspiration 4 or Polaris, and also how this involvement is changing over time? For example, between have you made any changes or adjustments between Inspiration 4 and Polaris?
So the Space Omics project in astronaut has been started with the NASA twin study about 10 years ago. And as a follow-up, we were able to find another opportunity driven by private company SpaceX. The Inspiration 4 was the first all civilian mission driven by the commercial company SpaceX, and which was a 3-day space flight. And Polaris is a follow-up mission of this Inspiration 4, and it is scheduled to launch this week, but has been delayed a little bit. But it will be the first commercial space work, the EVA, the extravehicular activity, driven by the Polaris the commercial company. And I may miss the final part of your question. Would you repeat again?
I'm familiar with these missions. I'm curious about your particular involvement on your project in these missions. And
so yes, throughout the astronaut multi-omics studies such as NASA Twins or Inspiration 4 and upcoming Polaris, we have found some specific transcriptomic signature driven by spaceflight, but we still need to disentangle which one is a major factor or which is a core factor. So this perturbation idea would help to understand the changes in the astronaut, the transcriptomic changes in astronaut, and we'll find the kind of core target.
Thank you very much for that question. And thank you, Janga and Kim, again for joining us today.
Thank you.
Right. So we're going to move on to the last research orbital launch funding applicant for today. So please welcome to the stage Madeline Hoy, researcher from Turney Lab. She will present her research proposal on studying the effect of microgravity on epithelial tight junction, highlighting novel mechanism of immune defect in space. So Madeline, when you're ready, please feel free to move on to the slide.
Great, thank you. So this project is looking at investigating the role of gravity in tight junctions, particularly with regard to their function in epithelial barrier. And so the epithelial barrier is normal epithelium serves a barrier function in your body cavities. This permeability of this barrier is regulated by proteins called tight junctions. In space, the tight junction proteins have been shown to break down. This disrupts the barrier function and can cause systemic effects, particularly because the epithelial tissue is so widespread throughout the body. We've calculated that this can play a role in up to 60% of the medical symptoms that have been reported by astronauts in space. So this really is something that's systemic and affects a range of systems here. We then have this need to understand both the timeline and the mechanism of this as a spaceflight specific pathology. The current approach to treatment on the space station is isolated symptom management. Each symptom is treated individually, but this won't work for missions as we go longer and further into exploration. Instead, because we want to avoid having this suite of specialized equipment to treat each symptom that comes up, we instead would like to move towards targeting an underlying cause of this, with the goal of simplifying the equipment that we would need and improving the astronaut health outcomes in flight. To this end, we've designed an experiment to better characterize this root cause of a range of our symptoms that we're seeing. So our experiment begins by inserting an intestine sample into a modified Ussing chamber. On Earth, an Ussing chamber is the gold standard for measuring our epithelial barrier function and is regularly used for probing tight junction disruptions. We make slight modifications for it to work in a microgravity environment. Over 7 days in microgravity, we will continuously monitor our barrier function and sample viability. This is really the critical component of our experiment, is this real-time functional monitoring, where we can see the effects of microgravity on that barrier function. Then, if available for post-flight recovery, we will freeze the tissue in flight and recover it on the ground for further structural analysis, looking at the tight junction proteins and the changes that have occurred due to the microgravity environment. Our key milestones for de-risking some of these methods include a timeline worst case analysis using benchtop clinostat simulations of microgravity so that we can see nominal and off nominal launch timelines and make sure that we're getting tissue viability for the duration of our proposed experiment. This will help us determine if we want to use a tissue or an organoid model for our sample insertion. We also plan to test our tissue freezing method in parabolic flight. And I do want to highlight that the tissue freezing method is not actually critical to the success of our experiment, in particular because these structural protein changes have been shown to linger for up to 2 weeks post exposure to microgravity. So even if our tissue freezing method ends up not working, we can remove that, do our freezing once we recover the tissue on Earth, and still observe these structural changes. The truly critical component is our ability to do this real-time functional measurement in microgravity itself. And that's where our team comes into play. We can leverage our team's, if our slide will go, sorry about that. Well, okay, we can leverage our team's expertise in doing clinical trial validation, benchtop simulations of these components, but more specifically, parabolic flight validation of this experimental method. So we have already shown in flight that the perfusion-based electrophysiology measurement, that modified Ussing chamber technique, does work. We can very confidently say that we will be able to record this functional measurement during the flight. So that's really a critical component here. And so the outcome that we're really looking for is to develop this this understanding of the tight junction disruptions that are occurring so that we can inform the development of a single point of care device for treatment of this 60% or majority of our in-space medical symptoms by looking at this as a root cause thing that is occurring due to the spaceflight environment. This will allow us to move beyond just doing isolated symptom management and towards holistic treatment of space-specific conditions. We can leverage some of the past human in space cohort expertise by looking at teams that have already flown organoids in the past to really address that tissue viability risk of our experiment. And we can then share the results with other projects, other groups that that might have tight junction involvement and not even know it in their experiments. Thank you.
Thank you very much, Madeline. Now we will move on to the Q&A part of this pitch. Yes, Ken Savin.
So the parabolic aspects of your study are really just to check the hardware, not to actually run the experiment per se.
Correct. Yeah. So we are testing the hardware components in parabolic flight. We don't have a long enough flight timeline in parabolic flight, a long enough exposure to microgravity to see the physiologic effects. So that's really where we need this orbital launch to be able to measure that. So we've tested them in phantoms and making sure that we can do the technology aspects.
That was a really great question. Thank you. Yes, Israel.
Yeah, hi. Great experiment. So one question is, what are you actually measuring? Is it like fluorescent reactions or some patch clamp, or what's the measurement? And the other question is, what effect can be to this measurement on things on Earth, like other medical conditions, not in space?
Yeah, these are great questions. So we are measuring the electrophysiology parameters. So we're measuring the tissue resistance and current flow. And so as the tight junctions loosen, we get more ion flow across the tissue. And so we see these parameters change. It's a pretty simple measurement in its core. On Earth, this is relevant to ion channel related diseases. So there are a whole host of these, including, for example, cystic fibrosis. So the clinical trials that I've mentioned our team has done are related to diagnosing cystic fibrosis and monitoring changes due to treatments. So any Earth-based disease that has a role of ion channels in it could potentially be impacted by this device.
Thanks.
Thank you very much. Yes, Patrick.
Thank you. In the very end of the pipeline, is it only this electrophysiological measurement, or there are some other measurements on Earth? I was wondering that, let's say that your method could be used for high throughput drug screening. that would need like sort of like a robust screening. So is there a bottleneck there, or have you talked about like a sample return from collaborators? How would you screen hundreds of drugs, for example?
Yeah, so that's definitely an area that we could expand into. We haven't explored it in detail yet, just due to kind of the constraints of FDA approvals and things like that for testing different aspects of the device. But this is definitely something that we would want to expand into.
Thank you.
Thank you very much. We have last question from Kevin.
Hi, good morning. You mentioned in the presentation that the cell freezing is not a requirement for success, but assuming you're doing your testing on ISS, you're completely subjected to either the Cygnus or the human-intended visiting vehicle timelines. So if your cell freezing doesn't work, what's the backup for getting your cell returns?
Yeah, so we can, anytime after the exposure to microgravity ends, we can still see those structural changes for up to 2 weeks. So the functional measurement, we think, will only last 7 days just for tissue viability. But if the tissue dies in microgravity, but stays in microgravity until it is recovered, that's still okay. Our 2-week timeline doesn't start until it returns to normal gravity environment.
Okay, great. Thank you.
Thank you very much, Kevin. Thank you, Madeline, again for joining us. Right. So we're now down to the last presentation for today. This team is applying for the equity investment. So it's a startup called Space Medipark that is based in South Korea. The company focuses on developing 3D bioprinting technology to produce organoids in microgravity environment. And we're going to invite to the stage Chan-Hung Park, CEO of Space Medipark.
Sure. Please share monitor.
Yes, we will be allowing you to share the monitor shortly.
Okay, thank you. Can you see?
Yes, we can see it clearly.
Okay.
When you're ready, please feel free to present your pitch.
Okay, it's a finish. Okay, I have so many moving part, and I'll first go on. Okay, I'm Dr. Bak from Sahalim University, working in Sahalim Medical Center. Our introduction is Space Mediparks. In my main third topic is teacher engineering in regenerative medicine, and we hold many of us patent related in this field. As you know, microphysical system MPS is based on this space bio study. We developed so many specific chip and MPS, and the 19 is IS launched is long chip with this UPenn. As you know, our focusing is a satellite-based MPS. Satellite-based MPS is deep space possible, and it can study high risk infectious diseases such as COVID, but it have to overcome its harsh space launch environment. Our ongoing project BioCabinet 25 will launched, and it's a bio 3D printing using IPS and the stem cell differentiation system. I will show this video. Our next is the ongoing project BioRex. It's a satellite-based return biomedical platform. Its the main focus is glioblastoma, very high risk is the cancers, and we evaluate it on the microgravity, and the new is the space drug. It's involved in Korean's big pharmacy. Our team is the 8 is the professor, and the 3 is engineer, and the 2 is clinician, and the 3 is the spatial biologist. And this is moving hours all of technical I show. Okay, in this field is massive is growth in is the market. It's our target is the satellite-based biology research consulting, and the fabrication is the field is our business model. And our milestone plan is this year's for this the venture status. But next year we have the plan to do found is the overseas with the overseas collaboration is the USA, and finally is the space MPS and the small satellite commercialization item. Our space Mediparis plan, this is ongoing, and the further is future plan. I hope to well going. Thank you.
Thank you very much, Shanham Park. We will now move on to the Q&A part of this pitch. Yes, Dr. Israel Biran.
Hey, thank you. Great presentation. So just can you clarify what's the business model?
Our business model is based on the satellite basis, the MPS, microphysiological system, and our core works in the small satellite, including the bio payload, such as the drug screening and the biology studies platform. Anyway, so our company is too focusing. Just is the MPS, including is the biomaterials such as the hydrogel. Is the we have the patent is the bioink, and is the tank free. Is CO2 independent media is very key technology. We can sell, and this is a good business model to study in the on space is cell culture, and another culture is the media. Is I think is some of our business is a key point.
Do you going to let pharma companies use it?
Yeah. That's right. This is our project is the glioblastoma. High risk is cancer is the study involved in Korea. Big pharmacy involved in new to develop the new space is the drug, such as the anti-cancer drug. And then this is the another my company's business field.
Thank you.
Thank you very much, Israel. Yes, Dr. Paul Kamoon.
Yeah, my question is concerning your 3D bioprinting. Do you do the 3D bioprinting on Earth and then you test in space, or do you do it in space?
Okay, it's a very good question. The previous is reported is bioprinting. It's a fusion deposit is the 3D printing methodology. Depend on the gravity, but ours is 3D printing totally different. It's the digital is a processing process. It's DLP. Using is the photo lighting technology, and short times I showed about our technology. We can make is very short time making independent is gravity, and then we make the another structure. This is the new 3D printer. It's with core Wake Forest, and we have the plan to the ISS launch schedule. It's the main is a liver 3D printing, hepatic 3D printing.
Thank you.
Thank you very much, Dr. Paul. We do have a question from our team. So could you further explain about the company's own IP and in any aspect that differentiates your product from other players within the bioprinting industry?
I cannot decide this time, but it's the our bio 3D printing is the some of specific is the printing is the field. Anyway, I have any ideas on the ground on space into both we can use, and the further is the our. But I have the my another company making a 3D printing and on ground. Anyways, and at this times I have no idea. Thank you.
Thank you very much. Right. Thank you very much, Chan-Hung Park, for presenting the wonderful pitch as the last presenter. Right, everyone.
Thank you.
Thank you very much. Right, everyone, that was the last pitch of the Humans in Space Virtual Pitch Day, Day 2. And I'm really positive that all of the proposals that were presented here today would be a transformative step in shaping the future of humanity in space, which is actually the ultimate goal of the Humans in Space initiative. So before we close, I just want to share with you important next steps under the Humans in Space Challenge. So the second round winners selected through the virtual pitch day, or today, will be having their final pitch at IAC Milan. If you're attending IAC, we highly encourage everyone to join us well on that day. And before we end, we would like to thank all the judges. So we will invite them to this. As you can see all of the judges on the screen. We'd like to thank everyone: Stephanie, Dr. Biran, Dr. Hollis, Dr. Savin, Dr. Kamoon, Cesar, Kevin, Martina, for all your valuable participation today. All the questions that you've shared and the insights that you have shared through these questions definitely helped us and the first round winners better develop their ideas. So we appreciate your time and your engagement here. And also thank you to all the first round winners for preparing such an amazing pitches for the event and actively participating in the Q&A session. I believe this is a very memorable step towards expanding the space healthcare field. And thank you again, everyone. You all make Humans in Space possible. Thank you very much, and hope you have a wonderful day and good evening to some people as well.
Thank you.
Okay, thanks a lot.